So, in this afternoon session, it is my great pleasure and honor to introduce you Nergis Mavalvala, Pakistani-American astrophysicist who made a great contribution in the first observation of gravitational waves. A professor from MIT, Massachusetts Institute of Technology of the United States. She is also a member of National Academy of Sciences of the United States. Professor Nergis Mavalvala is best known for her work in the detection of gravitational waves in the laser interferometry gravitational wave observatory LIGO project. But she has also obtained prominent results on other physics problems that evolved out to LIGO. For example, she has performed pioneering experiments on laser cooling of macroscopic objects in the generation of squeezed quantum states of light. Professor Mavalvala has a number of very important awards. And in particular, she has been awarded the Great Immigrants Award. The awards go to naturalized citizens who have made notable contribution to the progress of American society. And we all in our country are, I think, proud of her great achievement, contribution to the progress not only of American society, but of the world.
You're very kind.
Made a contribution in opening a new window in the exploration of the universe. Please join me to welcome Professor Nergis Mavalvala very warmly.
Thank you, Alex. Thank you. Great. So hi, everybody. Thank you for that very generous introduction. But for the rest of you, I'm just Nergis. And I'm going to tell you today that the title of my series of lectures is Gravitational Wave Detection, and the emphasis here is on detection. So I'm going to tell you about the detectors. I'm an experimentalist, unlike any of the other speakers in this summer workshop. So I'm going to have a slightly different take on most things, and most of all, you'll see my equations don't have indices. Sometimes I don't have equations at all, and if I could have brought my lab with me, I would have rather done that than bring a laptop, but in the meantime, you'll have to work with my laptop. Okay, so let me just say a few things up front. So in making these slides, I've actually borrowed and stolen shamelessly from many of my colleagues, and so some of their slides are included in here, and most of all, Peter Salson, who I'll introduce in the next slide again, but also some of my other colleagues. So Peter Salson I introduced in particular because if you like some of the ideas that I'm going to talk about, he's written a book, and this is the book. It's called The Fundamentals of Interferometric Gravitational Wave Detectors. That's a link to it. It's actually a great book if you're first getting started in the field and you don't know a great deal about gravitational waves and detection, even if you know plenty of general relativity and other topics. So that's sort of the materials that I've taken from. Now, I was inspired by a quote from Scott Hughes 2 days ago during his public lecture when he said, look, everything is driven by new data. And then I thought about that and said, yeah, and we make the data, so I should tell you about that. So all data, whether it's old, new, better data, is produced by exquisite instruments, whether it's gravitational wave data or anything else that you see where data that's hard to acquire is produced. It's done by an instrument, and usually by the best instrument humans can build. So that's going to be our task over the next 4 lectures I'm going to do, 2 today and 2 tomorrow afternoon. We're going to build some exquisite detectors. And I'm going to start just by telling you how goddamn exquisite they are, okay? So, an outline for my lecture is going to be, I'm going to talk about interferometers as gravitational wave detectors, and I'll talk about some subtopics there. I'll also talk about fundamental noise sources. In any experimental measurement, you cannot really speak about the measurement unless you know what the noises are and what the backgrounds are and what gets in the way. So we'll have to look at that pretty carefully. And then I'll talk about quantum technologies in particular. I'll talk about those not because I'm going to elevate them above some of the other noise sources in LIGO, and I'll do that for two reasons. The one is that they are actually, at the present moment in time, more important than other noise sources, and the second, of course, is that's what I work on. So for those two reasons, you will take a deeper dive into quantum technologies. Then I'm going to talk about third generation detectors, so not where we are now, but where we expect to be maybe 20 years from now. And I'm going to close out my lecture series with a current status. Where are we? You know, what is LIGO and Virgo doing right this moment in time? All right? So that's kind of the outline. I actually have never given this series of lectures before, so I can't actually tell you where lecture 1 ends and lecture 2 begins. We're going to do that a little organically. Okay? All right. So the grand challenge of gravitational wave detection. This is the thing that's going to set the stage for everything we're going to talk about. So I'm going to just take it as a given that we are tasked with measuring displacements or changes in length of 10 to the minus 18 meters. Both Scott and Bardry have given you many good reasons for that number, so I will take it as a given. So how do we do that? So we do that in LIGO by measuring the motions of mirrors using light. L in LIGO stands for laser, and when I say LIGO, most of the things I describe are applicable and in fact quite similar in Virgo, in Cargra, in Geo, and other gravitational wave detectors, but I'll just keep saying LIGO because it's stuck in my head that way, all right? So, the first thing we need are the test particles of general relativity, the test masses. These are typically the mirrors of the interferometer, and here is the scale of the problem. If I plop a mirror down here in this room and ask you how much it would move by, it turns out it's roughly a fraction of a micron, about 10 to the minus 6 meters. Now recall that this is the goal, 10 to the minus 18 meters, and that's expressed right around 100 hertz. So, that's my first factor of a trillion. I have to do something to quiet the motion of the mirrors from its normal, natural state of about a micron down to an attometer, okay? And what you're going to see is, as I develop the detector technologies for you, this is going to come from a number of vibration isolation and filtering techniques. And I think we'll get to that actually in lecture 2, I expect, okay? Now imagine we succeed at doing that. Imagine we succeed at making the mirrors of the interferometer still at the level of 10 to the minus 18 meters. Well, I will tell you that does you no good at all unless you also know how to measure such a small distance. And we make that measurement using light. That's the laser light, the L in LIGO. And there comes our second factor of a trillion. So the wavelength of the light that we use in LIGO is also of order a micron. Now what we need to do, in fact, is to measure 10 to the minus 18 meters. This is really equivalent of my saying to you, I give you a ruler, and the tick mark spacing of the tick marks on that ruler is 1 trillion times bigger than the measurement you want to make. Okay, that's the scale of the problem. And I'm going to show you how we come around that problem. And this is why I elevate quantum noise above other noises, because this is the problem of the counting statistics of individual photons. We don't count individual photons. We count actually many, 10 to the 20 photons per second. But even so, that's the quantum statistics of light will play a role. So now you should be convinced that it's worth sticking around to listen to what I'm going to say, because I'm going to show you how we're going to go from achieve these factors of 1 trillion in both the mechanics and the optics. All right? Okay. So let me just recap how the measurement is made. I'm going to go through this very quickly because Scott has told you about this in much more detail and has also reminded you of how not to be naive about it. But really, in the end, what we do is we look at the proper distance or the proper interval but for two particles that respond to a gravitational wave, and let's assume in this case the wave is coming in from the z-axis, so into the plane of the screen, and we can ask ourselves what would happen to two particles that are sitting at a separation x naught in my notation, L in any reasonable notation, and what you would find is that you can actually do a linear approximation to Einstein's equations for the metric perturbation, and in the x-arm you will get a quantity that's proportional to the amplitude of the gravitational wave and the spacing between the two test particles. Now you could repeat this calculation along the y-axis and you would get a similar expression, and then if you take the difference between the two, you would come quickly to this famous expression that we use all the time, which is that the change in length between particles is equal to the amplitude of the gravitational wave h, which is given here in its plus polarization by h plus, and the spacing between the particles. That sets the stage. Now, as an experimentalist, it's very hard to wrap your head around this particular kind of coordinate system where, with the calculations that I just showed and the ones that Scott and even Bardry showed earlier, these calculations are done in a coordinate system that are marked by the locations of the test masses, so they don't move. But as an experimentalist, I'm actually used to thinking about motion and movement and forces and so on. So you can also ask, do the mirrors really move? And it turns out that the answer is it depends on which gauge you do your calculations in. And so gauge freedom requires that all other reference frames should be equivalent, and so you can also choose what's called the proper reference frame, and this is a coordinate system that's described by rigid rods, and so the test masses are not tied to the coordinate system. The coordinate system is tied to rigid rods, and in that frame you will actually find that the test masses experience an acceleration from this tidal force due to the passing gravitational wave, and Scott wrote this in his lecture yesterday as well in a slightly different form, where you can see that there's a force that's due to an acceleration that depends on the mass of your test particles, on the separation between them, and then on a time varying piece of the gravitational wave amplitude. Right? So you can go interchangeably between either, but you should know that both are there, both work, and you can think just as comfortably in terms of the transverse traceless gauge, where the test masses don't move even though the space-time separations change, or you can go to this frame where the test masses will move. Okay? Either way is fine. So I think we are all convinced here in this room, given the lectures of the last couple of days and what I just said, that gravitational waves transduce a path length change. Now, what does that path length change look like? Well, for a plus polarization, you could think of a grid of particles like this, and I draw your attention to the center. At the very center, there's a particle, and as a gravitational wave comes by, you can see that it pushes particles along the y-axis further away from the center, and it pushes the particles along the x-axis closer to the center. Now, the other interesting thing about representing it this way is to notice that relative to the center, particles that are further away moved more. And that's exactly what we've said all along, that the change in distance between these particles is proportional to the amplitude of the wave and their distance. Okay, so you see greater separations there. Now, if you zoom in just on this center here at 3 particles, this is what it would look like, and you can see very quickly that I am now going to morph into an instrument. Okay? So think about, in that picture, think about the beam splitter as sitting at the center of that grid that I showed you. Now here is what we have for a simple Michelson interferometer. So we have a light source, and it's almost always a coherent light source. White light doesn't work very well because it's made up of very many wavelengths, and so you have to balance the arms of the interferometer too well. And we can talk about that more. It's not important here because we've always, from the very beginning, LIGO has had L in it because you need coherent light. So this is a scheme for measuring the relative motions of distance-free masses. The laser reflects off the beam splitter and reflects off the mirror here, comes back to the beam splitter. The other half of the light goes in this direction, and then here is the interference pattern. And what you see is you can actually write this out in terms of the field amplitudes and in units of the reflectivity and transmissivity of the beam splitter and the reflectivity of these two mirrors. And you get a field in the x direction, you get a field in the y direction, and the interference at the output is the sum of these two fields. And then most importantly, what we measure is not the field. We measure the field squared. We have intensity detectors. So we actually always measure the output power, and so that's the relationship that we'll have. Now, another important thing to notice is that this beam splitter is an object, and we're going to come back to the beam splitter because this is a classical beam splitter I'm going to talk to you about today. But tomorrow I'm going to have to tell you about a quantum beam splitter, and they're a little bit different. This beam splitter, there's a minus sign that comes here that's intrinsic to the way that beam splitters work. Beam splitters and mirrors in general, the way that you can get if you have an ordinary piece of glass and you shine a laser beam through it. Let's do it actually. Here's an ordinary piece of glass, and I shine a laser beam through it. I'm going to try not to blind any of you in doing this little experiment. How much of it is actually going to be reflected versus transmitted through the glass? Does anybody know, just for visible light, ordinary piece of glass? Close, 4%. That's the standard number. 4% of visible light reflects off of ordinary glass. If I want this piece of glass to reflect 50% and not 4%, the way I do that is I put an optical coating on it. And that optical coating, it comes with a phase shift. And that phase shift is represented in this minus sign here. So light that comes back to the reflex of the beam splitter from this surface versus that surface has a relative phase shift of pi. And that's where this minus sign comes from, okay? And that's really important because that's how you will recognize that the beam splitter has symmetry. It has a symmetric side where there's no minus sign, and an anti-symmetric side where there is a minus sign. And the reason why I introduced this to you is that in a lot of the literature, the output port of the interferometer is called the anti-symmetric port. And it's for this reason. This side sees the minus sign, okay? So we move on. We turn that calculation into an output power, and it turns out that averaging over time and doing a little bit of algebra, we can represent the output power as just the cosine squared function of the path length difference. K here is the wave vector of the light, so it's just 2 pi over lambda, which is the wavelength. And now you see, if you plot this power as just a cosine squared function, you very quickly see that this interferometer is a path length to brightness transducer. At the very bottom here, at this point, it's completely dark. Here you have half the light, and here you have all the light that you can have in the interference pattern. We're going to come back to this a few times. So that's sort of lesson number 1. The interferometer's job is it takes the gravitational wave, transduces path length difference. The light then in turn turns that into a phase shift, and the interferometer turns that phase shift into a change in power, just optical power. All right. So just to reiterate that, you can just see this is constructive interference. You get all the light, then in between slightly out of phase you get some of the light, and at the here you have perfect destructive interference. Okay. Now, the first task we have then, so you're now convinced that this interferometer should be able to measure path length changes. Now comes the next piece of the task for us, which is we have a signal, and that signal is the power variations that we measure at the output of the interferometer. Now we want to do some tricks to make that signal as big as we can. So the first thing that we notice is that I will declare that the light should travel in the arms of the interferometer for about half a gravitational wave period. And the reason for that is that if it travels for longer than half a period, then whilst the light is traveling in the interferometer, the gravitational wave has changed sign. It's gone, and you will wash out some of the signal. In fact, you can think of the most extreme cases when the gravitational wave period is exactly equal to the round trip period of the light. Then for every part of the light that sees a positive part of the gravitational wave, another part will see a negative, and they'll cancel completely, and you have no signal. So the ideal in this case is half a gravitational wave period. So now you ask about an interferometer that has 4-kilometer long arms that will translate into a round trip travel time, light travels at the speed of light, of 27 microseconds. Now, if you then convert that into these 27 microseconds into what's the frequency of the gravitational wave that this corresponds to, using this half period requirement, that would be a gravitational wave at 18 kilohertz. Now, most sources that we could imagine are not emitting gravitational waves at 18 kilohertz. In fact, we would like to have these detectors be optimized for detections of sources around, say, 100 hertz. So what can we do? Well, the obvious thing you would imagine doing is just make this interferometer a lot longer. How much longer? Well, you'd have to make it about 200 times longer, and that turns out to be quite expensive and difficult to do. So throw away that idea. So a natural thing to do is to think of some scheme by which you can actually have the light bounce in the arms. Okay? Now, this is not something that was invented purely for gravitational wave detection. In fact, if you've heard of the Michelson-Morley experiment, in fact, the second phase of the Michelson-Morley, Michelson first did the experiment and got to some sensitivity that was of order lambda over 5 or so. And then, so Morley came along later. And Morley was hired precisely to add more path length to the interferometer by folding the beams over many, by using multiple mirrors, and then they were able to get to a sensitivity of about lambda over 20, I think was where they were. Okay? So this is an idea that's been used before. I'm going to tell you of a more sophisticated version of that. Okay, and the sophisticated version of that is an optical cavity. And these optical cavities are going to show up again and again in the next few lectures. So I'll spend a couple of minutes on that. So the easiest way to think about an optical cavity, if you haven't thought about one before, is to just think about what happens when you put your own head between two mirrors. And you've all done that when you go to a trial room in a department store or something, right? They put multiple mirrors so you can see yourself from many angles, and you see multiple images of yourself, right? So this is the same idea, which is that you take two mirrors facing each other. Each mirror has to have some finite transmissivity so light can get in at all, at least one of the mirrors, and then the light bounces multiple times in this cavity. Eventually, you also need the light to get out. It would be a useless device if you could seed it with light and then not use that light anymore. And the transmission of the mirrors allows that. So this is really an interference device as well. It's, by the way, used ubiquitously in lasers. Lasers themselves use these kinds of cavities for the light to experience the gain medium of a laser multiple times. So anytime you want light to go through a device multiple times, this is a good way to do it. These are called Fabry-Perot cavities. And they have some nice interference properties that we can look at next. So now here is good. So here is how you should think about a cavity. I promised you I'd have no indices on my equations, and I do, but my indices are very simple as two mirrors, so they go from 1 to 2. But don't be scared of this stuff. Here, pay attention to this picture here. Here are the two mirrors facing each other. The dark surfaces are the coated surfaces of the mirrors. This is what makes a mirror a high reflector. Remember, if it was just a piece of glass, you only get 4%. In these mirrors, we are usually going for anything from 95% to 1 minus 10 to the minus 5. So 99.9999%. Because that's the kind of reflectivities we want, right? So they have these coatings. Here is an incident field. The field that's inside the cavity we call the circulating field. The field that's reflected we call the reflected field, and the field that's transmitted we call the transmitted field. And now, without belaboring the algebra too much, well, I'll just draw your attention to what happens to the field that's inside, that's circulating inside this cavity. And I have one other apology to make. This is the length L here is represented in the phase shift e to the I 2kl. It is different than this L here, which is supposed to be losses. Okay, so we can just you can ignore the losses. We'll talk about an idealized lossless cavity, so this big L here can be set to 0. Now what you see right away is that in complex notation, you have a field that's going to have, in the denominator, it has a term that depends on phase. And quickly this will remind you, if I took the absolute value squared of a field like this will look like a resonance. This will look just like any other resonance you've seen, where you have a numerator and then you have a denominator term that looks like some omega minus omega naught squared and some damping term. Okay? This is a resonator. How does the resonance actually come about? You can see that when this condition is satisfied for these phase shift, these fields are maximized, and that's a resonance. But really, let's forget about the algebra and think about the intuition here. So what happens is a light field is incident on this mirror. A little bit of that light, in this case, in the kinds of mirrors that we use in LIGO, only about less than 1% of that light goes into the cavity here. This is a high reflecting mirror. It only transmits very little. So when this light field has made one round trip and comes back here, it interferes constructively with the new light field that's come in one round trip later, and does that again multiple times, hundreds, some maybe thousands of times, and that's what builds up the light field in here. It's an interference process between the light inside the cavity and the light that seeds the cavity. Okay? And when you do that, then you build up a resonance, and it would look, before I show you what it would look like, let me introduce a couple of other terms. So the cavity finesse is the ratio of the decay time to the round trip travel time. Now in any oscillator, whether it's a mechanical oscillator, an optical oscillator, you always like to think about what's the quality of the oscillation. And how do you measure that? You measure that by saying, how many oscillations can I get before the amplitude decays by 1/e? Okay, we do that all the time. You must have done that even when you were in high school and did those boring pendulum experiments, right? The pendulum didn't go forever, and you could measure the decay time by measuring when the amplitudes have decayed to 1/e. Did you all do that? I had to suffer through that stuff, and that's why I became an experimentalist, I think. Okay. So that's a finesse, and in this case, in units of the reflectivities of the input and output mirrors, that's how you express finesse. It's a fancy expression, but really what you should know is it depends on the reflectivities. Why? Because the reflectivities are a measure of how many photons go back in the cavity as opposed to how many escape. So this is just a ratio of how long the photons live in the cavity and then escape, right? So it turns out then that finesse is also a measure of how many times a photon can bounce, and we call this the bounce number, and it scales as twice the finesse over pi, and that really comes out of just the algebra. There's nothing fancy or magical about it. So this multipass scheme, what it does is it increases the effective optical path length. So normally we write the phase shift of an interferometer as just 2 pi over lambda, that's k. Remember, the phase factor is just k times z. We write it as twice the length, because that's the path length it takes, and it's proportional to the gravitational wave amplitude h. And now I've added this bounce factor b, because now the light is like a folded interferometer. It bounces multiple times in the cavity before it exits. So that's the increased phase factor. This is what the cavity response would look like. I did it just for the internal field because I want to show you one special thing. This is the amplitude. So this is actually, take this expression, and this is the absolute value squared. So this is essentially the power inside the cavity. And this is the phase shift. So notice a few things. Notice the repeated pattern. This is just like any other interference pattern. Every time you get this phase condition here satisfies being 2 pi, you'll get a resonance, and same for the phase shift. And the other thing you should see is that these 3 different colored curves that I've drawn are for 3 different reflectivities of R1. I fixed R2 to be very high, just 10 parts per million transmission, and I change R1, and you notice that you can make a narrower, peakier resonance as the reflectivity gets higher. So the blue curve is for a 95%, 97% reflectivity. I chose precisely 97% because that's what we use in LIGO. And then the red and the green curves are for 85 and 80. And you see the resonance gets wider and the peak power goes down. So there's another lesson to learn. This is a device. When you use a cavity like this, that bounce factor B that I showed, which is twice the finesse over pi, is also a gain factor. The actual buildup of power inside the cavity is much higher than the laser power you actually seed it with. Okay? And in this particular case, that gain factor is around 130. So you have if you pump the cavity with 1 watt of power, inside the cavity at any given instant in the steady state, you have 130 watts of power. Now you might find this rather puzzling because I don't have any amplifier or gain medium in the cavity. And that's okay. All that I'm doing is instantaneously in the cavity I have more power. If I try to take that power out, I have no power, because what it means is I have to open up a mirror to do that, right? So it's essentially, you can just think of that as this is a driven oscillator, and just like any mechanical oscillator, at its resonance frequency it has a greater motion at the expense of having less motion at other frequencies. That's all we're doing. It's very much the analog of a mechanical oscillator that's driven. Okay, just at the resonant frequency you store a lot of energy, and then at all other frequencies you store much less. All right? Okay, so this is an optical cavity. Now let's ask the question of how do we actually make a measurement inside of LIGO. So let's go back to the Michelson-Morley experiment. So the Michelson-Morley experiment was a simple Michelson interferometer. That's what the Michelson interferometer is named for. And what Michelson used, as Scott showed, Scott, did you show that in your talk? I forget. You showed Michelson's device. The device he actually used to measure the output power was his eye. Okay? And so with this eye only, did I skip something? Okay, yeah, good. So with your eye only, let's go back to, let me draw on the board for a second. So this is I'm going to draw, this is the output of the power of the interferometer as a function of delta L. And here is what that pattern looks like. You know it's a cosine squared function. It's going to look like that. And the spacing here is every pi over 2 you get a maximum. All right? Or between a minimum and a maximum. So what Michelson had to do was he had to say, do I see all the light or do I see none of the light? And that would give you a resolution of lambda over, of pi over 2, which turns out to be a resolution of lambda over 4. That's what delta L would be if you had the only thing you could do is say it's completely bright or it's completely dark. And with an eye, you can do already better than that, okay? So here's what I'm trying to say here. So here's that output that I just drew. To go from bright to dark, you have a resolution of lambda over 4, where lambda is the wavelength of your light. And now notice what happens is that your sensitivity to H, which is your strain, is the same as delta L is equal to H times L, but now L is your optical length. It's not just the length of your interferometer, but it's your length of your interferometer times the number of bounces. And now if I could take my laser, and which has wavelength 10 to the minus 6 meters, I make some 200 bounce system, and I would say I can measure H of 10 to the minus 12. Okay? That's still a long, long, long ways away from H to the minus 22 that we want. Okay? It's 10 orders of magnitude. So what are we going to do? So we require 10 orders of magnitude more, and what it means is that we need to know much, much more accurately than totally bright or totally dark where on this fringe we are. Okay? And in fact, as I said, even our eyes can do better than that, but really in the end, we're not using eyes, we're using electronic photodetectors, and ultimately, the limit is going to come from the quantization of the light. So let me give you a very heuristic understanding of that. Imagine that I arrange to sit right here at this minimum, at the darkest point of my interference pattern. So you would say that the ultimate limit to the resolution is that if I had no photons coming, I had perfect destructive interference, no photons coming out of my instrument, and then I get one photon. That would be the ultimate resolution, right? Distinguish between 0 and 1. Now, we don't do that. These are not single photon measurements, and nor can they be. But even so, that's what we're trying to do. What we're trying to do is we're trying to go to the darkest point and try to resolve what's the, resolve to the level of the quantum fluctuations for that power. So I'm going to tell you what that is in next or in a few minutes. So I'll tell, is it next? Yeah, it's next. Okay, so now how do we understand that? So the next thing we do is we ask, well, what are the noise properties of a laser? So it turns out that a laser, the output of a laser, the photons are Poisson distributed. And what that simply means is if I had a photon counter and I just sat there and made it go click, click, click every time a photon arrived, these photons would arrive with a Poisson distribution. Okay? And of course, when you get large enough number of photons, that would turn into a Gaussian. But so, since it's Poisson distributed, we can immediately use the Poisson relationship to connect the fluctuations in the mean number of photons, and the mean number of photons is n bar. The fluctuations is square root of n bar. That's just any Poisson process will do that. And now we consider going to the interferometer operating at mid-fringe. So mid-fringe would be, say, right here. Now, why is that a nice place to be? Well, it's a really nice place to be because what we're ultimately interested in is measuring variations in power as a function of length. And you can see that over here, this is delta L, and this is delta P, and so the slope is the largest. So our dP out, dL, is the largest here. So that's a nice convenient place to be, okay? And at this point, we would have something that's half of the input power if we had perfect interferometer, right? Because that's the maximum and that's the minimum. So that would be half. It is P out over 2, but if you had a perfect interferometer, P in and P out would be the same because you're wasting no light. Of course, you don't have a perfect interferometer, but they're not bad. They're not bad. So you could do either way. But yeah, sure. Why don't we do that? Okay, good. All right, so that's where you'd like to be. So now let's just plug in some numbers. If you're at this place where you're at P out equal to 2, which is also P in equal to 2. Now the average number of photons that you have in any measurement interval time tau is simply equal to the energy of each photon divided by the total power. Okay? And you also know that the variance in the fluctuations in the number of photons then will scale by the square root of that, and that's what we have here. And if you then turn that into variations in your ability to measure path length, which is just the signal is given by the slope here, and your noise is given by the noise, you will get this formula, which simply says something that you've heard many times before from Scott in particular, that your ability to measure changes in length are inversely proportional to the square root of the power that you put in. That's what this says. Now, it's a simple, this is lots of formulas, but you can again be very intuitive about this. The intuition is simply your signal scales with laser power, your noise scales as the square root of power. So inevitably, your signal to noise ratio is going to be 1 over square root of power. Okay, that's what it says, and so that's what this says. So now we have some understanding of what's going to happen here. It says that wherever I am, I'm on the middle of the fringe here, I'm going to have fluctuations in the number of photons that are given by the Poisson statistics of photon counting that's going to cause me to jitter over here. That's the limit of the precision with which we can measure. And now I'm going to tell you one other thing that's going to set us up for the next thing we're going to do, which is that we would like to operate on a dark fringe, where P out is actually close to 0. So this is the place where we have the greatest slope, the greatest change in power per length. But it turns out, of course, this is where the power is large, and so our noise would be large. So we would like to go to where the power is close to 0. It's never exactly 0, but it's close to 0, because that's the place where you have the least amount of shot noise. Remember, square root of P, where P goes to 0, is very, very small. So that's what we'd like to do. So we actually do operate our interferometer here in this, at the dark fringe, and this comes at a price. And it's a price that I'll just tell you about, and maybe we'll get to solving it, but maybe we won't. The price, of course, is that now your power output is quadratic in the change in length. Right? So you have to now make a measurement of a signal that's not linear. Now I'll tell you we have that figured out, and we're going to do that, but I'm not going to tell you how we do it until maybe later, or maybe not at all, or maybe if someone will ask me a question. But because I want to concentrate on what are the limiting noise sources, this is a technical detail, I'll leave out the technology of how we do it, but it's important to know we measure at a dark fringe, okay? And it's very important for the next thing that we're going to do. All right. So I will skip this part of the generalized quantum limit just because I think I'm going to come back to it in great detail tomorrow. Should I do that? I'll do that. All right. Okay. So now comes the next piece. Remember, we stopped our discussion when we said that we needed to make a measurement of delta phi, the phase shift of the interferometer, that was 10 orders of magnitude better than this all dark, all bright measurement. Now, where are we going to get those 10 orders of magnitude? Well, now we're equipped to try and solve that question. We see now that the shot noise limit, this photon counting limit, tells us that our phase scales as 1 over the square root of the number of photons. And so we require 10 to the 20 photons in each 10 millisecond measuring interval. Okay? And that would correspond to 10 to the 22 photons per second. Now, why this 10 millisecond period? Everywhere that you'll see me using time domain units, I will always want to do things at the 10 millisecond time scale, because that's the inverse of that is 100 hertz, and that's where I quote all my sensitivities. So every time you see me going between time and frequency, the time scale is usually 10 milliseconds. So this then corresponds to 10 to the 22 photons per second. If I then plug that into what that means for the input power, that would be about 2 kilowatts of input power, 2,000 watts of input power. Now, this is more than virtually what any reasonable self-respecting laser can produce. Now, why do I say self-respecting laser? Because there are lasers that are out there that are used for machinery like welding and so on, where they can put out actually more than that. They can put out even 10 kilowatts. But they have terrible other properties. For example, their frequency has an enormous spread. They're not quite a white light source, but they're certainly not coherent over very long distances or time. So you don't want to do that. So getting to that limit needs a new trick. And now we're going to pull together all the things we've talked about. We've talked about operating on the dark fringe. We've talked about these Fabry-Perot cavities that are used to store light. And we put it all together, and you'll see how the interferometer actually works. So this is the simple Michelson interferometer. So the first thing that I will tell you is we arrange these two path lengths so that there is perfect destructive interference at this output here. So dark fringe, okay? Where's all the light going? I mean, energy has to be conserved in this device. Where's the light?
Reflected.
Sorry?
Reflected.
Reflected back to the laser. Okay? So when I set this up, all the light is going back to the laser. Now, add these two mirrors facing the two end mirrors, and these are the Fabry-Perot cavities that I told you about where the light bounces multiple times, and that gives me that extra factor of somewhere between 100 and 200. That's the bounce factor. That's the folding of the interferometer. And now comes the last piece, which gives me that boost of laser power, which is I add a mirror here. So all that light going back to the laser is bounced right back into the interferometer by the reflectivity of this mirror, and as a result you get a power buildup in this part of the interferometer that gives you about a factor of 50. Okay? And then you actually have some chance of getting to the 2 kilowatts of power you needed at the input here, which is that you start off with a laser that has something like 100 watts, and you have a gain factor of 50, and there you have 5 kilowatts. Okay? That's the trick. And without this trick, we couldn't do this. Right? So that's the, now it turns out that there are other refinements that I won't talk about, but this is the basic layout of the interferometer, and okay, so I just want to reiterate, it was the fact that we operate on the dark fringe. We decide to operate on the dark fringe because that gives us the least shot noise. But that was the thing that then enables us to use power recycling, because all that light is going back towards the laser then and not coming out at the detector. Okay, and so that's the power of shot noise. Now, let me just point out, this is a displacement noise spectrum of the LIGO instruments during observing run 1 when the first gravitational wave event was measured. And I just want you to notice that right here at 100 hertz, we actually, so this is in displacement. Anytime you have a displacement spectrum and you want to turn it into a strain spectrum, you just divide by the length of the interferometer, and that's 4,000 meters. And so what you see here is that indeed we have a strain sensitivity of 10 to the minus 23 at 100 hertz. Remember, our goal was 10 to the minus 22. That's what we set out to do when we made those numbers. And in fact, if the shot noise were larger, we wouldn't have seen that event. And in fact, we know that for a fact because we had shot noise that was larger by about a factor of 3 at 100 hertz during the first phase of LIGO, initial LIGO, and we didn't see anything. So this factor of bringing down the noise was very important, okay, for the detections. Okay. So there are many other design details that go into this. I'm not going to go through most of them, but I will tell you about a couple. So this now you're used to. You're used to seeing a Fabry-Perot cavity in each arm. Used to as in you've seen it now for all of like a minute and a half. This is the power recycling mirror, and they're just folded because these are long cavities, so you don't have to worry about the details of this. And then there's another mirror that has snuck in here, and that's called the signal recycling mirror, but it uses the same principle. The principle is that you have a dark fringe here, and it's dark only when there's no gravitational wave. When a gravitational wave comes by, it moves these mirrors differentially, and some light comes out. It has to be, otherwise we have no measurement, right? So the idea is that this signal recycling mirror then reflects those gravitational wave induced photons back into the interferometer to accumulate more phase. So it's another way of increasing the phase acquired by the gravitational wave signal photons. Okay, and the reason to belabor Fabry-Perot cavities, as you can see, they are everywhere in this interferometer, and use this trick again and again to enhance the number of bounces or the power buildup to make the instrument work. Okay, so I think this is a good place to take a break, and so let's take a 10-minute break, and then we'll come back to part 2. All right? Oh, before we do that, questions. Yes?
So, if we can bounce as much as we want.
No, we can't.
Why is 4 kilometers?
What's that?
Why are the arm lengths 4 kilometers?
Yeah, so the question is, we can bounce as much as we want, so why are the arm lengths 4 kilometers? So the answer to that is we cannot bounce as much as we want. Remember what limits the bounce. Remember the quantity I introduced called finesse? And the number of bounces is directly related to finesse, and finesse is directly related to the dissipation or the losses in the cavity. So realistic optics at that scale can't bounce much more than we're already doing. Okay, that's the sad but basic answer. Now in micro cavities or small cavities that you can build in a lab, you can get to cavities that are bouncing even 1,000,000 times. But for these big cavities, 4-kilometer long cavities means that the mirror, so here's something that I had on a slide that I didn't say. So what is the price that you pay for having these cavities? Well, one of the prices, there are many prices you pay, they're worth paying, but you pay them, is of course that you have to have mirrors that are bigger than the diffraction limited spot of the laser beams themselves. And so the reason you can't do a lot better in these long cavities is a diffraction limited spot for a laser beam that's traveling about 4 kilometers is of order a few centimeters. Okay, so it's about that big. And so that means to make a mirror that catches all that light, you have to make the mirror be 25 to 35 centimeters in diameter. And then to have low enough losses that every photon on every part of that surface bounces without loss is very hard. And in fact, tomorrow when I talk about when I bring it all together with whether the technologies that go in these interferometers, I will show you that the mirrors, well, I won't show you then, I'll tell you now. The mirrors of LIGO have a surface roughness over the full aperture of just about 1/10 of a nanometer. And that's already the flattest mirror you can make. You can imagine what happens if you have little roughness, photons just scatter off and you lose them. So another way to say this is that the losses of these mirrors over the full aperture is of order a few tens, 10, 20 parts per million. Okay, so for every 1,000,000 photons that hits that about 10 or 20 are lost, and that's pretty heroic. So you can't bounce forever.
How about if you use sub-Poissonian light instead of?
Tomorrow we will.
Okay, I
Yeah.
thought you could use anti-bunching,
Oh yeah, we. Yeah. So we don't use bunching or anti-bunching. We use squeeze states. So it's a cousin, but the same. So I'll talk a great deal about that tomorrow because that's in the quantum technologies part of my talk. So.
If no other questions, please let us.
Yeah. Oh, thanks. Good.